Hey guys, for calculus, this is a continuation of 4.4 covering topics in integration. We're going to cover the mean value theorem for integration. We learned that for derivatives. And then also what's called the average value, okay? So let's look over at this image. We know that integration tells us the area under the curve. So mean value theorem for integration states that if f is continuous from a to b and there exists a number c, right, an x value in between a and b, such that the actual area under the curve can be found, okay? So we're going to use this equation to find that c, that one spot where I can find the average area under the curve that is equal to the actual integral, that area under the curve that is given to you, okay? So every time I solve these questions, this left side of the work is a little lengthier, so I'm going to take a minute to solve this, plug in the answer here, and then solve this simpler side, okay? So let's look at this equation. My function is 9 over x cubed, and my interval is from 1 to 3. So step 1, I'm going to solve that integral. I'm going to say the integral from 1 to 3. And instead of saying 9 over x cubed, I'm going to bring that x cubed up with a negative exponent to make my life a little easier. Finish my notation with that dx, okay? So next step is I'm going to add 1 to that exponent. If I add 1 to negative 3, I end up at negative 2. Divide by that new exponent, I get 9 over negative 2. The integral from 1 to 3. Remember, you are allowed to put that coefficient on the outside and multiply to the answer of your f of b minus f of a. So I have negative 9 over 2. The function at b, so 3 raised to negative 2 minus 1 raised to that negative 2. Okay? So negative 9 over 2. So 3 to the second power is 9. That is going to get dropped down to the denominator because that exponent is negative. Minus 1 raised to anything is 1. So instead of saying minus 1, I want a common denominator. So I'm going to say minus 9 over 9. Okay? Now, let's say negative 9 over 2 multiplied by 1 minus 9 is going to be a negative 8 over 9. These 9s and negatives are going to cancel. So the 9s cancel and the negatives cancel. So I'm left with 8 over 2, which gives me 4. So again, this is just the answer to the left side. Now, I'm going to grab that 4, and if that's the answer to my integration, I'm going to say 4 equals my function. Here's my function, and I'm going to plug c in. So my function is going to read 9 over, instead of x cubed, I'm going to plug in that c, times b minus a, which here's my a and my b, so 3 minus 1. And now this is a simple algebraic equation, just going to solve for c. So 3 minus 1 is 2. 2 times 9 is 18. So I could say 4 equals 18 over c cubed. Multiply that c cubed over. Divide that 4. 18 divided by 4. I can also write that as 9 over 2. And now to isolate that c, I'm just going to do the cubed root. So c equals the cube root of 9 over 2. You can leave it like that. I encourage you to leave it like that. And that would be your final answer. That is the spot on the graph in between 1 and 3 that gives me the exact area under the curve, okay? Let's try it a little more complicated with a trig function. Okay? So again, Step 1 would be to do the left side of that formula, which is the integral from a to b of my function, which is cosine of x, and finish writing notation dx. Antiderivative of cosine is a sine. I'm finding that from negative pi over 3 to pi over 3. F of b minus f of a, right? Plugging them in. Now I'm headed off to my unit circle. Sine of pi over 3 is a radical 3 over 2. Minus, if I have a negative radian, it just means I'm going backwards. So I'm going into quadrant 4. Okay? And that value there gives me a negative radical 3 over 2. Two negatives make a positive, so I'm adding these, and I get 2 radical 3 over 2. Those 2's cancel, and I end up with radical 3. Okay? Now I'm going to plug that into that left side of that formula. Square root of 3 equals my function at c, so cosine of c, times b minus a. So here's my b, pi over 3, minus my a is a negative pi over 3. Okay? Let's write this as a coefficient up front. 2 negatives make a positive, so I add, and I'm going to have 2 pi over 3 times cosine of c. Okay? I'm going to divide this to the other side. When I divide by a fraction, I am multiplying by its reciprocal. So if I flip this, I'm going to have the 3 on the top with the radical 3 divided by 2 pi equals cosine of c. And now the way I isolate my variable c is I do the inverse operation of cosine. So I'm doing inverse cosine of 3 radical 3 over 2 pi. And that is what c equals. In this case, this would probably be a calculator question. You would have to plug that in. Make sure you are in radian mode, and that would give you 0.5971. And you are done with this question. When we did mean value theorem for integration, we were finding that spot C, which is an X value, that gave me the average amount, okay? Now, when we find average value, that keyword, guys, it will literally be written just like that. Find the average value. That is doing the same exact thing, but instead of finding the X, it's just finding the Y, okay? So, notice the other equation here had f of equals f of c times b minus a. So to find f of c, that y value, they're just dividing over that b minus a. So average value, think of back when you were in middle school and you were trying to calculate your grade. You'd add them all up, you'd find the total amount, and you divide by the difference. Okay, so we're just doing 1 over b minus a times the definite integral. Okay, so quick example. If I ask to find the average value, I'll give you a function and I'll give you an interval. All you're doing is 1 over b minus a times the integral from a to b of my function. Okay, and now you clean up this left side, which is 1 over 3. You do the antiderivative, okay? So if this was an x squared, now becomes an x cubed. I divide by my new exponent. 3 divided by 3 is just 1. I can leave it like that. Minus, this becomes an x squared. Divide by my new exponent. 2 divided by 2 is just 1. And I solve that from 1 to 4. So I have 1 over 3. And then I have my function at 4. So 4 cubed minus 4 squared, my function at b, minus my function at a. 1 cubed minus 1 squared. Okay, so again, I dropped down that 1 over b minus a, which was at 1/3. And now I did my antiderivative and then my function at b minus my function at a. I'm going to come up here just to finish cleaning. I have that 1/3. Okay, I have 4 cubed, which is 64, minus 4 squared, which is 16. Okay, minus 1 cubed is 1, minus 1 squared is 1. 1 minus 1 is 0. So we can ignore that part. If you catch it early on, you can eliminate it here. 64 minus 16 is 48. So I have 1/3 times 48. And that gives me 16. The average value is 16. Now, let's go on to another very popular concept, and it is, believe it or not, the 6th and last theorem you will learn in calculus, okay? And that is the second fundamental theorem of calculus. So it reads, if f is continuous on the interval containing a, then there are two things happening with the second fundamental theorem of calculus. One, the most important one, is that you are doing the derivative of an integral. Okay, remember that those are inverse operations. So notice that they end up canceling out. Okay, and you have from a number to a function. Instead of having both numbers, one of them is a variable. So they'll actually ask you to do the derivative, or you'll see it written out. The derivative of an integral and a number and a variable. Okay, now notice that that x goes in the place of the t in both of them, and again the derivative and the integral cancel out. So step one, they're asking you the derivative and the integral cancel each other out. So notice that right here canceled out, okay, because they're inverse operations of each other. And two, you're going to plug that function x in the place of t, okay. Remember that dx means, d means the derivative of x. So I plug that function into both spots. Now, it is irrelevant what that number in the spot of a is, as long as that number is in the bottom and the variable is in the top. Okay? Remember when we talked last video about properties, I told you may need it. If for whatever reason the number's on the top and the variable's on the bottom, you need to pause, flip them and pull the negative out, and then you can keep going. Let's check out some examples. This first example reads, evaluate the derivative of the function. So if I want to have this left side read derivative, I'm going to put an f prime. And then this right side, I have to apply the derivative. My next step is that a derivative and an integral will cancel each other out. And this function up here replaces the variable in the integral. Make sure, most students always forget this second variable over here. So I have cosine of x times the derivative of x. Well, in this case, the derivative of x is just 1. So I have cosine of x times 1, which is just cosine of x. Okay, so it may seem insignificant to plug in that x into this dt because it does disappear, but you're going to see this next question when it's something more complicated than just an x. So this one said it to you in the wording to do the derivative. Here it's written in the expression. Solve the derivative of the integral. Again, derivatives and integral cancel out. It does not matter what that lower number is as long as the number's in the bottom. And then I'm going to plug this into both variables. Now just be very careful with your algebra. I have square root of x squared, and then don't forget this squared, plus 1 times the derivative of x squared. So this here cleans out to the square root. An exponent to an exponent I multiply, so I have x to the 4th plus 1, times the derivative of x squared is 2x. And probably a cleaner way of writing that would be to put the 2x in front of the radical. And we are done with this question. So as I look at this next question, notice that the number is in the top and the function is in the bottom. Okay, when I showed you that property of flipping these two and pulling out a negative, I told you it wasn't mandatory for solving a regular definite integral, but the rule for second fundamental theorem of calculus says that the number has to be in the bottom. So this is one of those times where it's going to be needed. So I'm going to rewrite this as the negative derivative of the integral, and now that I pulled out that negative, I'm allowed to put this number 26 at the bottom and this 3x up top. And now I'm allowed to finish this. The derivative and the integral cancel, and my function 3x gets plugged into both variables t. I'm going to come over here. I'm going to have 2 times 3x squared minus 4 times the derivative of 3x. Okay? Here, just be very careful with your algebra. Remember that that exponent of 2 gets applied to the 3 and to the x. So I have 2 times 3 squared is 9, x squared is just x squared, minus 4 times the derivative of 3x is just 3. Okay? So now the 2 and the 9 are going to get multiplied, and that's going to give me 18x squared minus 4, and then all of this times a 3. I have a 54x squared minus 12, and I'm done cleaning this. So now let's take a look at some lookalikes, questions that may or may not be the second fundamental theorem of calculus, okay? And make sure you don't get tripped up with these on the test. So the first question, I have just an integral. I'm not being asked to do the derivative, so automatically I know that it is not a second fundamental. And here I'm just going to solve plain and simple my definite integral. My second one is probably the trickiest one to see, because if you notice, my third has the derivative of the integral and I have a function. It's clear that this one is second fundamental. But this one has a variable, but it's not asking the derivative, okay? This is one of the main ones we're going to focus on today. This gets solved just like the first fundamental, just like the definite integral. So let's take one at a time. Here, my first step is to do the antiderivative. If I have x to the first, it now becomes x squared. Divide by that new exponent. Plus antiderivative of 2 is 2x. Solving this from 2 to 3. Next step is my function at b minus my function at a. Okay? When I clean this, 3 squared over 2, I have 9 over 2 plus 2 times 3 is 6 minus 2 squared is 4 divided by 2 is 2. 2 times 2 is 4. I get 9 over 2 plus 6. Distribute this negative. 2 and 4 both make a negative 6. So these two, negative 6, is going to cancel out with this positive 6. And my answer is just 9 over 2. So here's an example when I get a numeric value. Okay? Let's look at this next one. Let's follow the same exact steps here, okay? This is first fundamental theorem of calculus, not second, because I'm not asking for the derivative. Step 1 is the antiderivative. T to the first becomes t squared divided by that new exponent plus 2, and my variable is t that I'm working with, and I know that by this dt. And now my f of b is a function, right? So all I'm doing is instead of plugging in the 3 like I did here, I'm going to just plug in an x squared. So I'm going to have half times x squared plus 2 times x squared. There's my f of b minus f of a. Now I'm plugging in this 2. And now just clean. In this problem, because I have a variable of x, instead of getting left with a numerical answer, I'm going to get left with a function. So an exponent to an exponent, I multiply. I have half x to the 4th plus 2x squared minus, this is going to end up the same as this one, right? 2 squared is 4. 4 divided by 2 is 2. Plus 2 times 2 is 4. Okay? This makes 6. So my final answer is just going to be half x to the 4th plus 2x squared minus, this gives me 6. All right. And our last example, when we do have the derivative of an integral, derivatives and integrals cancel. My function gets plugged into the variable t. So I have x squared plus 2 times derivative of x squared. Derivative of x squared is a 2x. And I'm going to write that in the front of my answer, x squared plus 2. And now just distribute. So 2x times x squared is 2x cubed plus 4x. 3 different examples that look a lot alike but are solved 3 different ways. Let's take a look at this integration word problem. Very simple and straight to the point. A chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where time is only existing from 0 to 60. Okay, that means that chemical is only flowing in from 0 to 60 minutes. Find the amount. That is our key word right there. Find the amount. That's what's letting us know to do an integral. Find the amount that flows in during only the first 20 minutes. Actually, I'm going to underline first because that lets you know to start at 0. The first 20 minutes. So I'm doing the integral from the first 20 minutes of that function that represents the chemical flowing in. And then don't forget your notation of your dt. And that's what you're solving. That's probably the hardest part, is figuring out the information from the question. Next step is do my antiderivative. So I have 180t plus, this was a t to the first, so it becomes a t squared. And now I divide by my new exponent. And I'm going from 0 to 20. It's always a nice day when that bottom number is 0. It's going to make my work nice and easy. So I'm going to have my function at b minus my function. If I plug 0 into this t and 0 into this t, it's going to cancel all of this out, and this will all equal 0. Okay? So now 180 times 20 is 3,600. Okay? Plus, I have 20 squared. So 2 squared is 4. Add that 0 in, okay? Those zeros. Divided by 2 and multiply by 3, I get 600. Which gives me an amount of 4,200. Now, please don't forget your units. This says that we were pouring in liters per minute. That means in minutes 0 to 20, there was a total amount of 4,200 liters poured in of chemical. All right. Let's look at some more vocabulary that you're going to be seeing in these word problems. So anytime they're talking about a derivative, they're going to talk about a rate of change or a velocity. Some of the words we're going to be seeing with integration, we just saw the amount. Displacement is another example. And net change is another example. And I'm going to show you visuals for that in just a minute, okay? Displacement, think about if they ask for how much, let's say how much did a car travel from my house to my friend's house, you can also say how far was my car displaced from my house, okay? And a net change, net means like a total amount of change, okay? Now some vocabulary that will be seen mentioned with velocity. If velocity is positive, greater than 0, then that means the object is moving to the right or moving up, okay? Now this is on a graph. Visually, it's seen by being above the x-axis. If my velocity is negative, okay, we'll see that below the x-axis, it means I'm moving left or down, okay? And if my velocity equals 0, meaning an x-intercept on the graph, it means that my object has stopped moving. This is going to be huge when we start talking about motion soon. Make sure you get these notes down. Let's take a look at a visual to help make sense of all this. If I drove from my house to my friend's house, let's say halfway through that drive, my friend says, hey, pick up some food for us. I backtrack a little bit to a fast food joint I just saw, and then I keep going to her house, okay? So I'm going forward, I go a little bit back, and then I keep going to her house, okay? Displacement subtracts that backtrack that I did, so it could just tell me how far am I displaced from my house? How far is my friend's house from mine? So let's say, remember we said above the x-axis is velocity going forward, okay? So I drove forward amount to her house, I backtracked to go get food, and then I kept going to her house. When you talk about displacement, how far am I from her house? It subtracts that backtrack that you did because that doesn't tell me how far the distance is from my house to her house. Now, total distance traveled is not talking about how far out are you, but it talks about what was the total amount that you drove. So notice that even though this one counts your backtrack as a negative, total distance traveled counts it as a positive. And for that reason, the notation of the integral has an absolute value on the function of the velocity, right? So I drove forward, I drove back, and I drove forward. Total distance travel counts that negative traveling as part of your distance, where displacement does not, okay? Let's see if this starts to make a little more sense down here. Pretend I'm standing at my desk, okay? Let's say I take 10 steps forward, that's like the positive direction, 5 steps back, and then 3 steps forward again. So I drew you here a number line. I took 10 steps forward, 5 steps back, and 3 steps forward. Let's say my desk is right here. Displacement asks me how far am I currently displaced from my desk after having taken the 10 forward, 5 back, and 3 forward. Well, if you look, if you add 10, subtract 5, and then add 3, I am 8 units or steps, let's say, away from my desk. So displacement is how far am I? I am 8 steps away. Okay? Total distance traveled asks me how many steps did I take in total. Even I'm going to count the ones I took backwards as a positive. I have 10 plus 5 plus 3. I took 18 steps. Okay, and you can see that down here in a graph visually, and it's very important to understand these graphs because a lot of times in the AP test, they'll just show you the graph and expect you, so from this graph, they'll say, how displaced were you? Well, you have to take that bottom part as a negative. 10 minus 5 plus 3 gave me the 8. But then if I ask for total distance traveled, I'm going to count that negative. That's why you see the absolute value in the integral as a positive. I took 10, then 5, then 3 steps to make a total of 18 steps. So I'm going to use this last question to not only talk about the difference of displacement and total distance traveled, I'm also going to use it to show you an example of using your calculator for these questions. On the AP test in multiple choice, you have 15 questions that are calculator and 45 that are not. 30 that are not. It's 45 total. And then in the FRQ, out of the 6, you have 2 that are calculator and the rest are not. So this is going to be very useful. The first question says a particle is moving so that its velocity is given by that function. It's measured in feet per second. Question A says, what is the particle's displacement? Okay, so we know displacement is just a basic integration of the function. And then they're giving you your integral here as being from 1 to 5. Okay, so I'm going to do the integral from 1 to 5 of this function given. I'm going to say t cubed minus 10t squared plus 29t minus 20. Okay, and my notation, please do not forget your notation. Being good on notation just lets those AP graders know that you know what you're talking about. This is in terms of t, so I'm going to write dt. Okay, now your first step on your calculator, again, hardest part is really just interpreting the information, is I'm going to go into my y1. Y1 is right here. And I'm going to plug in that function. Now, your calculator only has one variable to work with. I know there are a bunch of letters down below, but this variable x is the only variable you have to work with. So I wrote it in terms of x. Okay. Next thing I'm going to do is I'm going to change my window from 1 to 5. I don't really need the visual right now, but when we go to our graph, you see this button window right here? I'm going to change my minimum x to be 1 and my maximum x to be 5, okay? But for now, we don't need that. I'm going to go second mode because the word quit is right there. It takes me to my home screen. And now I'm going to press alpha window, and notice number 4 says integral. So we plugged this guy into y1, and now I'm going to press on the home screen alpha window 4. Okay, you see the little boxes it gives you? It literally just set this up for me. Okay, so I'm going to go from 1 to 5, and now you can waste your time and rewrite this entire equation, but you have this equation written in y1. So you're going to click alpha, trace, and y1 appears there, and whatever equation you have plugged into y1, it's going to put in that parentheses for you. And since the variables that I wrote in y1 were x, I'm just going to put an x here to finish off my notation. You press enter, and there is your answer. Now, I don't know about you, but I'm not a big fan of decimals because that could be an estimation. I'm always going to check to see if there's a fraction version, which would be much more accurate. You find that by clicking math, and number 1 says frac, stands for fraction. So it's going to convert your answer to a fraction, press enter, and it gives you 32 over 3. 32 over 3. So this particle was displaced. It moved 32 over 3. Let's label everything properly. Feet. And because it was a positive answer, it moved to the right. Okay. All right, let's check out this next one. B says, what is the total distance traveled by the particle from 1 to 5 of the time? Again, the time is in seconds, so it's from 1 to 5 seconds. Total distance traveled from 1 to 5. So on the last page, we said that total distance traveled is the integral of my time, which is from 1 to 5, of the absolute value of velocity, which in this case, sorry, I'm already writing v of t. My absolute value of my function, and my function is t cubed minus 10t squared plus 29t minus 20. Okay, close your absolute value and finish off your notation with a dt. Okay, now the whole concept of the absolute value, let's look at the graph for a minute. Okay, we still have this plugged into y1. I already fixed my window to say from 1 to 5, and now I'm going to go to my graph. Okay, I already had it loaded, so it popped up, but for you, it might take a minute to draw it. Notice that I have a portion that's positive and a portion that's negative. So that previous answer of that 32/3 took this positive amount and subtracted it by this negative amount. Now with total distance traveled, I want to add this amount with this amount, okay? So if I can find out what this x-intercept is when I switch to positive to negative, I'm going to show you two different versions of solving this, okay? So let's do second trace. It says calc up top. And I'm going to click 0 because I want to find when I hit that 0, when I hit that x-intercept. It asks for a left boundary. As long as you're to the left of it, press enter. Then it asks for a right boundary. As long as you're to the right of it, you're good. Press enter. And it asks, guess, please, yes, give me the answer. When you press enter, it says 0. So what you're really looking for is to find the integral. Remember, this is already listed as y1. So I'm going to do my integral from 1 to 5 of, let's call it y1. Not 1 to 5, sorry. We just said 1 to 4. dt. Plus, we're going to add the absolute value of this negative portion down here, which goes from 4 to 5, okay? So this is one way of solving it, okay? You are finding each of those amounts and making sure you get the absolute value of your answer, okay? So if I go to my home screen and I go to alpha window 4, I can go from 1 to 4. I'm not going to put the absolute value yet. I'm just going to put y1 by saying alpha trace. And I'm going to put dx, because again, in y1, it's in terms of x. This gives me 11.25. I'm going to do my math frac. Now, it gave me a positive answer. That should make sense to you because on the graph, that left side from 1 to 4 was positive. It was above, okay? Now, if it wasn't, I would take the absolute value of it just in case. Now, let's do that same thing. I'm going to scroll up, press enter on it so I don't waste time retyping everything. But I'm going to go from 4 to 5. Now, whoops, I put 45. There we go. Just click delete on the 4. Now, if I remember, according to this graph, this is below. So this answer should give me a negative. And check it out. It does. I'm going to press math frac. I get negative 7/12. But remember, I want total distance traveled, so I'm taking the absolute value. Okay? So press alpha y equals, and you can create your own fraction, or you can scroll up, press enter, and then I'm going to add the positive version plus. So let's press alpha y equals. And over d stands for numerator over denominator. And I want the positive of 7/12. Because again, absolute value, total distance traveled. And I get 71/6. Okay? So now, that was option number 1. Option number 2, and this is really nice by your calculator. You're going to tell me, why didn't you just show me this first? I want to make sure you see the visuals and understand it all. Is that I can plug this all in at once. Okay? So I'm just going to do the integral from 1 to 5. And now I'm actually going to plug in that absolute value of y1. Okay? So basically, if I were to draw the absolute value, it's going to flip this up to the positive and already count it as positive. Now, where's that button for absolute value? Let's put our alpha window integral. Okay, I'm going to go from 1 to 5. And in here, you're going to click math. And you're going to scoot over to the right to where it says NUM for number. ABS stands for absolute value. Press enter. And bam, you have your absolute value bars. Now click alpha trace to put your y1. Put your variable of an x. And it should give you 11.8333. Again, we don't want all those long decimals, so I'm going to press math frac, and it should give me the exact same answer of 71/6. Now, I didn't do it last time, but let's do it this time. My total distance traveled, I was traveling in feet per second, so this is feet. I traveled a total amount. Remember, we're not going to write right or left here because we did go a little to the right, a little to the left. With total distance traveled, it doesn't care what direction you went. It just cares how much you traveled in total.